Okay, we're going to talk about gravity again, and I want you to remind you of this equation. The force of gravity between any two objects is related by this equation. But we have forgotten one piece, the big G on the end. Now, if we look at what this means, this force, this is weight. And it's equal to mass times gravity. So, in essence, this is set equal to this, right here. Okay, right up here. So, let's just do that real quick. So, if we look at m little g, which is 9.8 on this planet, and we look at big G, which never changes, and we look at m1, m2 divided by d squared. Now I want you to remember, when we're talking about the Earth, this is the mass of one object. This would be the mass of the Earth. Earth. ME. Now this object is the same as this one over here. So now you do some algebra, and G resolves to m1 m2 divided by d squared times this crazy constant that we've been dealing with, G. So it doesn't matter how big m1 is, okay, because it's gone, canceled out of the equation. When we do this math, the m1 is gone. So we end up with G, mass of the Earth, divided by d squared. And that is why all objects follow this equation. All objects. So the mass of the object cancels out. And that's important for you to see. Now I also want you the idea of a field. Okay? We talk about gravity, we're talking about a field. So here's object 1, and here's object 2. Okay? Object 2, we're going to make it bigger, is 3, if this has mass of m, this has the mass of 3 m's. This has a field around it, a gravitational field. And as you get further from the object, it gets weaker and weaker. This one also has a field, but because this weighs more, it has a stronger field at a further distance. So when we look at the interaction between these two particles, the 3m is attracting the m with a force. The m is attracting the 3m with a force. But we realize that not all poles are equal. Not all poles are equal to individual objects. So in other words, it's like the Earth and the person problem. Yeah, a person falling to the Earth pulls on the Earth equal to what the Earth pulls onto the person, but this is a big old rock, and it doesn't get affected as much as the person does. So when you think of the gravity between you and Jupiter, for example, even though Jupiter is the biggest planet that we have in our solar system, because of the distance, you aren't affected by Jupiter. You are affected a little bit by the moon, even though it's much smaller because the moon is closer. Let's think about centers of gravity, for example. I'm going to draw the Earth with a hole driven through it, and I'm going to put a person here, that's going to fall in this hole, and they're going to drop through the hole. What happens is, on the surface, they weigh g. Okay? And this is related to the distance between the person and the center of the earth. When they're at the center distance, g is equal to 0. When they come back to this side over here, they're at g again, of course in the opposite direction, or negative g. So what would happen to a person in a situation like this? They would fall down, gain some speed, shoot past, get accelerated at g again, head on back, same thing, head on back. They would be like a yo-yo bouncing from in and out of the planet the whole time. And this experience would take place as long as any outside forces aren't there to stop them. So when we look at how fast, what's g here? Well, the distance is reduced. And remember g. G equals big G, mass of the earth, divided by d squared. And right now, we are messing with d squared. Okay, I'm trying to get that to be e there. We are messing with the distance. We're decreasing the distance. So when I'm standing on the surface of the earth, I'm a radius away. But now I'm inside the earth. I'm much smaller. Okay, so that is an issue when you talk about gravity, is how far you are from another object. Let's just talk briefly about weightlessness and weight and all of that kind of thing. If I am flying in an airplane, okay, we're going this direction. My feet are on the floor of the airplane, and essentially the airplane is being held down by a gravity field. Okay, and I am included in that gravity field. I am still attracted to the center of the earth. If for some reason the plane decides to take a nosedive and drop, the floor is actually pulled away from my feet, although I have inertia, so I want to stay still. So what could happen is I could float. I could float up and down. And when I float up and down, I incur what we would call weightlessness. And you could have the same thing in an elevator. If I am in an elevator, and here's the scale that I'm standing on, like a bathroom scale, and the elevator goes up, it's going to squish or compress this scale, because the floor is going to be going up, pushing on that scale, and it's going to compress that scale and give me a higher reading. If it goes down, the floor is actually going to pull away. My inertia is going to try to keep me still, and it's going to make that scale expand, which gives me a lower reading. It's kind of like what you would experience when you are on a bathroom scale, and if you would touch the wall and pull up or down, you can make the scale move. Same thing in an elevator. You would experience, if for some reason this elevator would go into free fall, it's going to fall at 9.8, you're going to fall at 9.8, everybody's falling at 9.8, you are going to experience weightlessness. Weightlessness is any time that you are not experiencing 9.8 meters per second squared, not attached to anything. Okay, so I go over a roller coaster. The roller coaster goes up and down. I'm in the car of the roller coaster. As it approaches the top, it tends to throw its objects up in the air. And for just an instant at the top, you may experience 0G, because what's happening is you're being accelerated upward at 9.8 meters per second and downward at 9.8 meters per second squared, and now all of a sudden you feel queasy in your stomach because you have just experienced weightlessness. Astronauts have to train to deal with weightlessness because it is something that your body doesn't necessarily care for. There's some hardwired fear and flight things that go on when you are weightless that are not good. So that is weightlessness, and that is the final thing that we want to talk about when we talk about gravity. Again, we've shown the math that shows that G is not dependent on the weight of the object. And if an object is experiencing a vertical G and a downward G, it is weightless. If an object is in free fall, okay, and not pressing against anything else, it's essentially a balanced situation. However, it is moving, and it'll also give you the appearance of weightlessness or no weight at all. So that's the second gravity lecture. Thank you.